Today we begin the last chapter that I had in mind for this course, and that is chapter 6, combinatorics, which as you know was voted by you in a survey I sent out a couple of weeks ago. And this was by far the most popular topic out of all the ones that I had. And it is probably also the most useful one in terms of other areas that are way broader than just mathematics. So, for example, the previous chapter is very useful if you want to learn how to write proofs and if you want to maybe study courses like real analysis in the future. But combinatorics is something that you're likely to encounter or use in many other fields, even beyond mathematics, even computer science. There's a lot of things about computer science that are um, whose foundations is basically some variation of combinatorics, some variation of these ideas. And so this is quite important, quite interesting. And we're going to, as always, use this topic as an excuse to learn new techniques, since writing combinatorial proofs has somewhat of a different flavor to other stuff that we've done in the past. But nevertheless, these ideas are always connected. So it was previously established in this course, and I don't remember exactly what lecture we saw this when we were talking about set theory. There are always k to the n, maybe I should write n to the k functions from a set of size k to another set of size n. And we used this combination log analogy to argue why this is true. I want to talk a little bit more about why this is true, and then we can start considering variations of this problem. So for example, and we've already seen examples of this, like I said, with the log, the dial, but let's do something maybe a little bit more concrete. Let's say that we have a set of 4 elements, all distinct, right? So what would be if I take this set and I find all possible ways of selecting 2 elements out of it, right? So if you don't like this notation, then as usual, we can include the 0, 1 instead of 2. So what is this set? What is the size of that set? And more importantly, actually, now that I think about it, maybe I want to do the other example first. Okay, so let's consider x to the 0, 1, right? Okay. So, you know what? Let's just not do this abstractly because this is an example. In how many ways? Many ways can we choose elements? Let's say 2 elements. Let's start with a simple example. 2 elements from X. Now, this question isn't very precise yet. We need to make this more precise because what do I mean by choose? What constitutes a valid choice? So let me make a table here. So one possible way of choosing 2 elements from X is if I just use the same element twice. I haven't said that I'm not allowed to use repetition, so maybe I can specify that with repetition. With repetition, meaning repetition is allowed, and I'm also counting the repetition, right? So using the same element twice counts as a different instance, right? But of course, I can combine A not just with itself, but with B, with C, and with D, right? Similarly, the element B can be combined with A. And now you notice that I'm distinguishing the elements BA, the choice BA, from the choice AB. I don't want this to be conflated, so the order matters. Maybe I can add that as another specification. And with order, right? So I'm taking two aspects into account. I want to consider all of these possibilities. It will be CA, DA, B. You can probably see where this is going. The diagonal consists of the ones that have repetitions. And if you take the diagonal as a symmetry axis, then indeed you get all possible combinations if I'm not accounting for the order. We got BC, we got B, D, C, D, C, B, D, B, D, C, and D, D, right? So maybe you already knew this, but of course we have 4 times 4, which is a total of 16 possibilities, is the answer for any set of size 4, choosing 2 elements at a time, right? Another way of thinking about this is that this is just x to the 2, x squared. All the functions from the set 0, 1 to a, b, c, right? And this is how I'm making this choice. Okay, any questions so far? What if I don't allow or don't want to count repetitions? So any way of choosing 2 elements out of a set of size x is basically the functions from a set of size 2 to x. And this is telling you what the choice is. All possible ways of making this choice, right? So 0 means I don't include it, 1 means I do include it. And so this function would be saying how I can make this choice, right? Another way of thinking about this, this is basically just the same as x cross x, right? It's all the tuples, the pairs. And the pairs, of course, can have repetitions. A comma A is a valid pair. And I am counting order. A comma B is a different pair than B comma A. So these are 2 different ways of looking at the same thing. I don't know if I want to leave the equal sign since if I'm very strict, they're not the same set, but of course they are the same idea. So if I don't want to count repetitions, just eliminate. That's not how you spell eliminate. The diagonal, because the diagonal is the one that counts the repeated element, right? Okay, so I don't think I have to include this, but maybe I can just say if I color the diagonal in red, maybe this hopefully helps visualize what is going on. Now, what if I don't care about the order? So ignoring the order, and by here I mean AB should not count as different because they are the same elements, right? If I don't care about the order, I shouldn't distinguish this. Should not be, or let's say, instead of counting different, let's say, should not be distinguished from BA, right? So this, if I write this in bold blue, this is the selection. And if you think about it, I only have to consider the top right triangle, including the diagonal, right? So this would be all the choices without order, but with repetition. And finally, the final way of choosing this is, of course, if I just take the top smaller triangle, this would be not counting the order and also not counting repetitions. So this choice in very bold gold is no repetition and no order. And these are all the ways that I can choose this. Repetition is the same as replacement in this context, yes. Okay, so it seems like I have four different things that I'm counting. The first one we already formalized and proved, and that is that in total, there are n to the k functions from k to the n. I just gave you an example with 4 and 2. But of course, the other ones seem a little trickier to count, even though you can use your geometric intuition to devise a formula to count how many of these elements there will be, right? Because you always know the size of the diagonal. Things become tricky, including the geometric intuition, of course, when I am no longer picking two elements, but possibly more. And for bigger sets, this doesn't become very obvious. So the first thing we want to do is talk about how we're going to make sense of this. Now, the whole square consists of all functions from 2 to 4. You can think about when I add a certain restriction to this function. For example, if I want it to be surjective or injective or bijective, then of course the count will change and this will mean something. You will explore this in a combination of the tutorials and the problem sets. So for now, let's focus on counting specifically what we mean by this. Okay, so we already know. Let's denote some notation. We know, and this is, by the way, not very universal, so I will try to only focus on the things that are universal and for the problem sets, right? So I'm not saying, and not everyone uses the same notation, but that is fine, right? So we denote by permutations with repetition and k. I always mess up the parameters, so I will try to be consistent with this. The number of permutations we can, for now, just call any sort of choice. The number of choices of a set of size n. Permutation. Okay, wait, let me add this like this. The number of choices we denote by PR the number of choices of k elements from a set of size n with repetition. I want to count repetitions as well. And with order, meaning I distinguish things that have the same elements but in a different order. Similarly, PR stands for permutation with repetition, so maybe I can include some other notation. Actually, before I do this, maybe I can just write the first observation, remark, maybe proposition. So we already know that P, R, and K is always n to the K, right? Because this is basically just the functions from K to N, right? So there's nothing more to say. Is it the same way I wrote it up here? N to, yeah, N to the K, right? Because every function is making a choice of K elements and the set, the codomain from which you're picking the elements has size N. So there's nothing else to do here. And I just gave you two different, very different examples and different approaches of arguing why this should be true. Now let's look at maybe some more sophisticated things, right? So the next definition is P denote by P and K the choices, the number of choices of n elements, sort of k elements. Um, Let me see if this makes sense. Okay, elements. And wait, excuse me 1 second. Okay, maybe you can't hear it, but my neighbor started drilling, so that's why I had to close the window. Number of choices from k elements from a set of size n with no repetitions, but with order. Okay. So how do we calculate this number? We're trying to pick the choices. So if this box denotes the first choice, the set has size n. So we have n possible elements to choose from. For each of those choices, we have how many elements in the next one. If I'm not allowed to do any repetition, then I have to exclude whichever element I picked first. These numbers must be multiplied because for every choice of the first one, I have n minus 1 choices for the second one, right? So these numbers must be multiplied. For the third choice, if I'm not allowed to repeat the first two elements, well, I have to exclude those from my possible choice. So I only have n minus 2. And I do this until I have chosen 1, 2, 3 k elements, right? Because my choice consists of k elements. So the last one, and I'm pretty sure I'm not going to write this the correct way, should be n minus k plus 1. Oh, it does. It does make sense, right? So the next proposition is I want to argue that P n k is the same as this number. And how do I denote this number? Well, this is n times everything, but only up to a certain point. So a very succinct way of writing this is by using factorials, right? So this could be n factorial, and I have to divide out by whatever I don't care about obtaining anymore, which would be n minus k factorial, right? I think I never properly defined what the factorial means, but we've used it plenty of times, and it is a very that one is indeed universal notation. So please let me know if you want me to to add any detail here. If you wanted to prove this formally, just the idea, since I don't want to overwhelm you with being overly technical, I think is unnecessary. The argument in green is good enough for proof in the context of combinatorics, but if you really wanted to formalize this, you should use induction. And the fact that if you want to calculate how many permutations with no repetition and with order there are from k to n, wait, did I write? Yeah, k to n, then if you knew how many you can find by having removed just one element, then this is n times that number, right? And this makes perfect sense because that is exactly what I wrote down in green. So in the induction, this would be having removed one element. And now when you add that element back, well, you have n new choices for each of those choices. So you have to multiply them. It's the exact same idea. I just didn't necessarily write this in an inductive way, right? So the proof isn't the crucial aspect of this. The important part is how we make sense of this intuitively. Now, how can we understand this in terms of other objects that we defined in the past? Well, that will be your task to figure out in the problem sets. Okay, now let me see what else is worth. Oh yeah, okay. There's one more important thing I want to define. We don't have to give every single one of these choices a name, but there's one that is very important. So let X be any set. Now you remember that the power set of X, denoted in this way, is the collection of all subsets of X. And we also know, because we proved it I think even in different ways, that this set always has size 2 to the 2 to the size of X, right? Even if it's infinite, regardless of the size of X. But this is always true. So I think right now, just for the sake of not complicating notation, let me just think about finite sets. Most of the combinatorics that we will talk about will be on finite sets. Anyway, everything we've done so far is only applies for finite sets. So my question to you is, out of all these sets which contain everything, out of all these sets, how many of those sets have a given size? Right? So I don't want to consider the collection of all sets. I want to count, since I'm considering choices of a fixed length inside a set, it makes sense to ask the same thing for subsets, right? So let X be any finite set, denote by nk, right? The number, let me erase this since we don't really need it. Okay, let me change the notation just a little bit. I apologize for making so many changes. Let X be any set of size n, so that this notation makes sense. We denote. And this is read as the number is n choose k, or the combinations of n in k. There's different notations, but the one I included is, I think, pretty universal. And this is the size of, you take every a inside the power set of x, or let's just say any subset of x, but we want a to have size k, right? So this is our definition. People define this in different ways, maybe equivalent ways, but this is our definition. It is, in my opinion, the purest definition, because this is what this is supposed to represent. Um, since this one is actually more important than the ones above it, let's include some examples, right? So what would be n in n? What would be n in 0? What would be n in, let's say, n plus 1? I've never said who k or n is with respect to each other, right? They're just two natural numbers, so there's no reason for them to be related in any way, according to my definition at least. N in 0, n in 1, and is there another obvious one? Okay, so the first one is 1. Give me 1 second. Okay, I'm already getting some good answers. So what is this? The only set, because it's a finite set, right? So the only set that has the size of the whole set is X itself. So there's only one choice. There's only one subset that has 0 elements, which is the empty set. So there's also one. What about the next one? The next few elements. Okay, so according to the chat, people are saying 0. Indeed, there are no subsets of n of x that are bigger than x. because of something that we proved, right? The inclusion mapping proves that this is impossible. So there aren't any elements in the set. There are no subsets that are bigger, right? But notice that our notation makes perfect sense even in this case. Okay, what about the last one? Exactly. So this is just a set of singletons. So if I really wanted to write this, I could just write it in this fashion, right? X, capital X. And how many elements, how many singletons are there? Well, as many as elements, and this is the thing we're calling n. Maybe just one more example. What if I do write a number that's smaller? What do you think this should be? And after this, I want to tell you how to calculate this number. And now that I think about it, there is a small detail that I skipped. Okay, so according to the people are saying in the chat, this is also n. Indeed, how do you fix a subset of size just one fewer than the set? That is taking the set and removing one element. And for that element, I have as many choices as there are elements in n, as in x. So this is still n, right? Because it's the same count as before. You can actually prove something slightly more general, and maybe I can leave this as an exercise because it's very easy to prove, and even easier after the proposition that I'm about to prove, but maybe you can try proving this using a bijection just from the definition, right? So don't use the following proposition because that proposition makes this obvious. So the exercise would be, if you want to think about this, in general, this is always true. Why is this true? Because if you think about what we are doing, maybe something here is in order. What is happening, right? So this is x, and x is some set. And what I'm doing is I'm choosing some elements inside x. So if you imagine x, the elements of x as being small circles, then choosing, let's say, 3, I have to color 3 of these elements, and the question is, in how many ways can I do that? No repetition. I cannot color the same point with red twice and consider that something different. The order also doesn't matter, right? Because I am not choosing the order of these 3 red dots. They're just 3 red dots. So in how many ways can I choose this? Well, if you think about it, whenever I color 3 things in red, the rest of the elements that I didn't pick are not colored in red, but I could just color them blue. Because why not? I mean, these are just colors, right? These are just things that we are imagining, right? And so choosing 3 red dots is the same thing as choosing blue 4 dots. Sorry, four blue dots. And this is how you get the difference because here k is playing the role of 3 and n minus k is playing the role of 4. So the combinations of 7 and 3 is the same as 7 and 4, right? Does that make sense? By the way, another observation that is not that trivial to prove from the proposition, but it is trivial from the definition, in case you're interested, is that if you add all of these up, you get the power back, right? So if you take n in 0 and you add it to n in 1, and you add it all the way to n in n, after this it's all 0, right? So there's no point in keep adding. Then this is all possible sizes of subsets of x. So this will give me back the total subsets of x. This is obvious, like I said, from the definition, because these are just counting subsets. So if we count all possible sizes of subsets, well, we get all subsets, which is the power set of x. So this is a remark that is obvious. If you defined this symbol, the choose symbol, differently, then this fact might not be that obvious, which is why I prefer doing it this way. Now, the most important proposition of this lecture is, of course, can we say in general, can we get a formula? So when K shouldn't be bigger than n because otherwise this formula will not work. Then who do you think this will be? And this shouldn't be too difficult to prove from the things we already did in the past. But there is in fact a formula, which I'm sure you've seen, which is this one, right? Now, the correct way to prove this is not to do this from scratch, but to use things we've done before and use the information about functions, right? What's the connection between functions and subsets? Now, there is something that I wrote which is kind of wrong. So let me just fix this. So this proposition, of course, we also need k to be less than or equal to n, right? Otherwise, the formula doesn't make sense. I mean, we can still define the number of choices, but it will always be 0 if this happens to not work out. You cannot choose k elements from a set with no repetitions if the set has size less than k, right? If you have 7 objects and I tell you pick 18 out of them, but don't repeat, well, that's impossible because you only have 7 of them. If I pick 18 different ones, I would have to repeat them, right? That's something that we will talk about more on Thursday. It's known as the pigeonhole principle. Right now, let's just add this restriction so that the formula makes sense. And by the way, this also tells you something interesting about the factorial numbers, but let's worry about that later. Okay, any questions so far? Is there anything that I haven't covered? How do we prove this? And again, we could prove this by induction or something weird, but let's use the thing we already have. Let's use the intuition to derive this maybe slightly more complicated formula. Why are there this number of subsets of size k in a set of size n? How did I come up with this? And if you think about this, this formula is very similar, looks very similar to this one. Where is it? Right there. So if I'm choosing k elements with no repetitions and no with the order, then how do I relate these two ideas? Let's focus on this for the rest of the lecture, and then we can call it a day. This will be covering pretty much half of the notation that I'm going to need. It might be useful for me to add a special case that you might find interesting. So let me add that here, and in the meantime, try to think about where I get all these weird formulas from. Let me add one special case. So here's what should be the mark? In the special case, when k is the same as n, meaning I'm picking all the elements. I am taking into account the order, but I'm not allowing, I mean, in this case, I cannot have repetitions, right? Because I'm picking, I mean, sorry, I could be picking repetitions, but I'm not because I don't care about repetitions. So in the special case where I'm picking all the elements of the set, then Pnn would be in this case what? N factorial over n minus n factorial. We can agree that 0 factorial is 1 for reasons that will also become evident soon. But this, you'll agree with me, is just n factorial. So this is called the permutations of n, or of x if I'm talking about a set x, right? Am I talking about a set x? Yeah, I mean a set of size n. So in this case, these are just called the permutations, not the permutations of k and n, just permutations, right? Maybe I can include one simple example of what a permutation is. I mean, we already have an example up there, but this is maybe more particular, right? So if my set X consists of the elements, again, A, B, C, what are all the possible permutations of X, right? So what are the permutations? Permutation, again, it means that I am not allowing repetition, but the set that I'm picking, I am choosing 3 elements. I'm picking all of them, right? Okay, so if we pick them in the order that I wrote them down, well, this is one repetition, sorry, one permutation. I could just switch C and B out because these are different. I am considering the order, right? It says up here with order somewhere. With order, right? But no repetition. So AAB is not a valid permutation. So ACB, A, sorry, not A. Another would be CBA, CAB. What other ones am I missing? Okay, so in the chat, someone's asking if n. All right, n factorial. Yes, I think you were answering my question from earlier. Thanks. All right, so if you believe the proof that I wrote using induction, then this should be 3 factorial because the set has size 3, and 3 factorial is 6. So I should have 6 permutations, and right now I have 4. So I'm missing 2. I'm missing the ones that start with B, right? C, A, B, and B, C, A. And these are all permutations. A permutation is just a rearrangement, right? You're just taking the elements and putting them in a different order. I'm taking into account the order, I'm not allowing repetition, and I'm using all of them. So this is just a shuffle. It's a shuffle of the elements, like a shuffle of a deck of cards, right? If a deck of cards has 52 cards, well, there's 52 factorial shuffles. And there's a nice explanation as to why this number is way bigger than your intuition might suggest. So I might send that to you later or talk about that on Thursday. You may have seen that before. It's not it's I don't know, it's very common knowledge. Okay, so now we talked about permutations. We talked about permutations of smaller size. We talked about combinations. Oh, by the way, I should call this. We denote n choose k, also called combinations. Okay, so now you know the difference between combinations and permutations, right? Combinations don't care about the order because it's just a subset. Permutations do care about the order. Okay, so now you should be able to tell me, how do I prove this fact? How do I connect these two ideas? How is this in any way related to the permutations? Let's let's try something. Maybe writing this formally isn't as valuable in this case because the proofs are very simple, but the idea is the one that has power, right? So let's think about it this way. This is X, and X will contain some number of elements A, B, C, D, E, F. And right now I want to pick 3 of them. So I have a box for the first one, a box for the second one, a box for the third one, right? So in the first one, I could pick any of these, let's say B. Let's say B. And the second one, I cannot pick B because everything that I'm talking about is not considering repetitions. But maybe I can pick D. And for the last one, maybe we can pick A. So this is a choice of 3 elements, right? Now someone might sneakily say, wait, I have another choice for you. Why don't you pick B, A, D? But if this is a set, if this is a subset, then these two are the same. Deleting the thing I don't want to. These two are the same set because they consist of the same elements. If I wrote them in a different order, well, that doesn't change the fact that these are the same set. But how do you see how these two ideas are connected? One is a permutation of the other. Permuting a set doesn't change a set. Okay, so exactly, Yang is suggesting in the chat that we divide out by k because that's how we eliminate the order. And indeed, that is the idea, right? So the idea, the key concept here is that these two are just permutations of each other. But it's the same set. So if I'm counting subsets, then I'm overcounting. And how much am I overcounting? Well, for each set, I am including all the permutations of that set, and all of those are the same set. So for each choice, I'm overcounting by 3 factorial. So I have to subtract 3 factorial for each of these numbers. And the easier way of doing that is just divide by 3 factorial, right? Okay, so the proof, if I want to write this formally, is to observe the following. If you take n to the k, this tells you how many subsets you have. And if I count all the permutations of each subset, this gives me exactly the number of permutations of n in k. Is it n in k? Like I said, the parameters, I always mess up the order. N should be below. Actually, I don't like this anymore because now the binomial coefficients are in reverse. Okay, it doesn't matter. Doesn't matter at all. Okay, so does this make sense? For any subset of size k inside a set of size n, if you include all the k factorial permutations of it, that gives you all the ways that there are to select k elements out of n without repetition, counting the order, right? Since we have like 8 minutes left, instead of me giving a theorem or something, let's maybe try to understand this even better by writing out an example. Maybe we can code one, but this will take a little longer. Okay, let's just say it this way. Or should we just expand the example above? So from above, X is the set A, B, C, D, E, right? F. Wait, did I skip something? A, B, C, D, E? No, it's fine. From above, we have that set. So how many ways can I do this? Let me think about this. I think this will probably be way too big. Let's eliminate this. So this is a different example because otherwise I'm going to spend much longer than the time we have left. So what would be 4 in 2, right? And how many ways can I pick 2 elements here? Okay, so if I pick no repetition, so A is not allowed, but I have AB, then AC, then AD, and that's all the choices that involve A. Then I also have all the ones that start with B, right? So I have B, A, B, C, B, D. And for the next one, I have C, A, C, B, C, C has repetition, that one doesn't count. C, D. And I wrote this in a weird way, but anyway. So these two are overcounting, right? Every pair is being overcounted. Actually, why am I missing some? Oh, I'm missing sorry, DA, DB, DC. Okay, now it makes sense. So this is all the ways of counting this. So it's 3 by 4. So unless I mess something up, this should be 12, which is the whole table, right? But if I just want the sets, then A, B, and BA are the same set. The same elements written in a different order, but it's the same set. So these two are equal as sets, right? Similarly, AC, maybe let's put a circle. AC is the same as this one. BC is being overcounted because it's the same as this one, right? Same goes for BD. Now, DA is being overcounted with this one, and these two are also the same, right? So every single one of them is paired up with another one because there are 2 factorial ways of reordering each of these sets as they have 2 elements, right? So if I divide by 2, I get the correct number. So like I said on this, we made a mistake. In this example, if I wanted to compute out of a set of size 4, how many pairs can I find, not accounting for the order? Well, that's 12, but divided by 2, because everyone is counted twice in this table that I just wrote down, and that should be 6. And that indeed should be 4 factorial over 2 times 2, right? Okay, so I will stay here for the next 4 minutes should you have any questions. I know this might be quite basic, but let me know if there's anything confusing, because we will use this as building blocks to get really complicated things. And also, an exercise that I would suggest you do, try thinking about all of this again in the context of functions. Where does injectivity or surjectivity play a role? For example, up here, a permutation is the number of bijections, right? Because a bijection is you're not allowed repetitions, that's injectivity, and you're using all the elements because k is equal to n, so that's surjectivity. So the number of permutations is the same as the number of bijections, right? Two different names for the same thing. Try to connect these ideas with others, and as you'll soon see in the problem set once it's released, um, all of these ideas are connected. Okay.